Yep. So we start off with learning how to describe things going on in a circle. Okay. So in a circle, right, we no longer just interested in things like distances and so on. We are more interested in the angle, right? Because you're going in a circle, you're repeating the motion, okay, in cycles. One cycle is 360 degrees, okay. And hence, right, a useful descriptor of motion of this type that repeats itself is something that is called the angle. Now you learn angle, right, in the case of a circular motion, it is very easy to understand because you indeed see a real angle that is opening up, okay, as part of the circular motion. The mathematics that describe angles in circles, right, however, also apply themselves, right, to oscillation, because just like circular motion, oscillations, right, repeat themselves. Okay, just like me also, I repeat myself. Yeah. So the theta, right, the angle is hence a very important descriptor. This is just math. How to theta relate to S over R. You got to last time, right, when you learn this, probably you don't appreciate it so much, right? That the theta in radian, we don't use radian enough. But radian is actually super useful because, right, it gives us a ratio, okay? So what is this ratio? For a theta, right, for angle theta, when you express it in radians, right, it's a ratio, arc length to radius. Yeah. So if you want to know, right, let's say if I have an angle of radian, of 1 radian, then it simply means, right, that particular arc is 1 radius because need to divide by radius, yeah. And about 6.3 radius makes up the circumference, because 2 pi r, 2 pi r divided by r itself, right, gives you 2 pi, which is 6.3. Yeah, so one circle, right, the full circle is 2 pi radian. Okay, so the whole circumference is about 6.3 radius. Conversion, I'm sure you know how to do that already. Next, right, we describe the angular velocity. Angular velocity, right, the average form is simply, right, some later angle minus the initial angle, or we denote it by a change, yeah, and divide by the time. So this is like common. Or another way of writing this, right, is just like that. Yeah, the average. And what about the instantaneous? Instantaneous, right, is simply the derivative. Okay, so all these are borrowed concepts across the whole physics. And here, right, is where it starts to get interesting. How do you relate, right, this omega, which is not difficult to understand because, right, it's just telling you how fast, right, is the angle being swept, okay, at a particular point in time. Or it's not saying just, right, what is the angle being swept across, okay, divided by the time, is how fast is angle going to be swept at a point in time. So that's a rate. How do you relate, right, this rate to the velocity, okay, of a particular object performing circular motion? Is this formula? Because, right, you see, what are our 2 building blocks? First building block, right, is S equals to R theta. Second building block, right, is omega equals to d theta over dt. Yeah. You combine these two together, right? Let's say you take ds over dt, which is velocity. Then, right, you differentiate the right hand side, right, of this. So say ds over dt. Then you will have r. How does this look like a? Let me change the pen. That one look like a for calligraphy. Okay. Then this one will be r d theta over dt. So this is r omega. Okay. So that's where it comes from. B equals to r omega. And this is a super useful equation. And I am actually quite surprised, right, across many years that many a time, right, when people do this topic, right, they actually forget this formula. Okay. Once you forget this formula, or the rest of the topic, right, no game already. Because a lot of the equations, right, when you deal with acceleration later on, you'll be always playing with two versions of the same thing. Okay. And the two versions of the centripetal acceleration, right, come about because of v equals to r omega, or you can convert into the two forms through this equation. So this equation is very important. Okay. Next, right, since we are talking about things going on in a circle, we can associate something called frequency, okay, to the motion, especially, right, if the motion is uniform, then this frequency is more meaningful. Yeah. So it's simply, right, 1 divided by the time taken to finish one cycle, and this is otherwise called as known as the period. Yep. And here, right, we can hence relate, right, the angular velocity with period as well. And once again, right, this must be for uniform motion. Okay. Why so? You see, if the omega, right, is if it's a non-uniform circular motion, it goes faster some part, slower some part, right? Then there is no fixed omega. The omega is at different part of the circle is always different. Okay. So this omega equals to 2 pi over t, right, must be for uniform circular motion, not general. Yeah. So with these basic tools, right, we can go on and learn more about this topic. Okay. But first, right, we need to return to Newton's laws, right, to help us, right, appreciate some of the fundamental tenets of circular motion. First question, right, is can an object as traveling at non-uniform speed, right, accelerate? This one is straightforward, okay? Because, right, if it's traveling at non-uniform speed, the speed is changing. Therefore, right, there will be a change in velocity. You see, why so? Because, velocity, right, is your vector. So it has a magnitude and direction. Yeah. So for A, right, is simply talking about the magnitude changing. Yeah. What about B? Can something moving at constant speed, right, be accelerating? Answer is yes. Okay. Because, right, now we look at the second property of velocity, right, of a vector. If the direction is changing, then, right, the velocity would be changing. If velocity is changing, right, then there will be acceleration, because acceleration is dv dt. So once there is a change in velocity v, then there will be acceleration. In fact, you need an acceleration. Okay. So this comes from where? This simply comes from Newton's first law. Because an object, right, will continue with a constant speed in a straight line if there's no net external force acting on it. Okay. So the net external force, right, must be there to change its direction. And how large is it? Okay, it's equals to the Newton's second law, F equals to ma. Yeah, or rather, right here, it's not clear. Don't know why. F over m. But let's be mindful of this thing. Okay, here, right, you normally don't write the arrow sign, the vector notation, right? But here we're going to write it because, right, we're going to appreciate, right, how centripetal acceleration, right, the direction is always, right, the same as centripetal force. And what is it? Okay, we'll derive it. So the long and short of this portion, right, is to put this at the back of our mind. Every time, right, we see a situation whereby velocity is changing, or we must be very conclusive to say, right, that there must be acceleration. Because once again, right, after some time, maybe near exam, you may still realize that there are some students who ask, why must there be a centripetal acceleration since the speed is the same? Yeah, because this is a very common question, because they cannot appreciate, right, that velocity, right, don't just alter speed, it alters, acceleration don't alter speed, it alters velocity. And velocity is made out of speed and the direction. So two things, yeah. Okay, now, right, let's dive in deeper, right, into what happened in a circular motion. We have this particular scenario here whereby a particle is moving at a constant speed, okay, but the velocity is not the same because direction is slightly different. So let's consider, right, these two positions, position A, right, and position B, slightly off or away from each other by an angle d theta. So we could write the following about this distance that it has covered. Okay, so hang on, let me think what I'm trying to say here. Oh yeah, okay. So let's look at the bottom diagram first. This triangle here. If we want to figure out, right, what is delta V, okay, delta V, right, is always equals to final minus initial. But in this case, right, we are dealing with vectors. So we are actually talking about a final vector minus the initial vector. So the final, right, is actually VB or minus VA. So let's figure out from this diagram, right, how does VB look like? So we are looking for this arrow here, which is VB. Then minus away, right, this horizontal arrow, which is VA. Okay. Then, right, you do your vector addition. So you take this one, VB plus minus VA. So the VA, right, we must flip it around. Yeah, so how do you add these two vectors? So when you add these two vectors, right, you will have VB plus minus VA. Yeah. So the result, right, will be the third side, the missing side. Okay. So this is your delta V. So let's figure out, right, what is the angle inside here. This angle inside here, right, is the angle between two tangents, okay? Because the velocities are tangential to the circle, right? And tangents are always 90 degrees to the radius. Oh, am I right? So if, right, the two radius have an angle of d theta between them, or d theta between them, then the two tangent must have the same angle d theta between them. Oh, because the tangents are perpendicular to their radius. If the radius are off by a certain angle, the two tangent must be off by the same angle. Okay, so this theta must be the same one as the angle subtended. Okay, in that narrow slice there in the circle. So now, right, this delta theta, right, how large will it be? Well, we can use small angle approximation, right, to help us. For example, when you have a normal triangle, okay, or a circle. So this is like part of a circle, right? When the angle is very, very small, then, right, this up here, right, okay, let's call it delta S, okay, and this R. This delta S, right, will be equals to R delta theta. Am I right? And for small angle, right, this is simply equals to theta. Okay. This oh no, I don't need. Oh yeah. So that this small angle, right, will let me say again. Whether it is small angle or not, right? The arc length is always r d theta. But right, when it is a small angle, the arc length, right, will be almost equals to the triangle, the flat line here, the straight line that connects the two points on the circular arc. So arc length, right, will be equal to the straight line that connects the 2 points as well. Okay, for small angle. Do you catch this part? You see, for these 2 points, right, that's on the arc. By right, they are connected by a curve. Okay, but when the theta is very small, right, this curve will approximate to become a straight line. So it is the same, right, as the chord that connects those 2 points. Yeah. So arc length equals, hang on, this thing is not writing too well. Chord length. Yep. So in the same spirit, right, this delta V, right, is equals to V delta theta. Okay. So with that in mind, right, we can go on and solve, right, what is the centripetal acceleration. Because, right, now that we know that delta V is equals to this, so you know, right, that the acceleration, right, will be equals to delta V over delta T. Yeah. Okay. And that is equals to the V delta theta over delta T. And that will be equals to V omega. All right. For the very small angle delta theta lah. So there we have it. So this is the formula for centripetal acceleration. Yeah. If we substitute V equals to R omega, right, into this equation, then you will get, right, A is also equals to R omega square. If you substitute the other form, omega equals to V over R. Sorry, yeah. Accidentally press the tab button, brings us out of the whole page. Yep. So here, right, it gives us the other form of the centripetal acceleration, V squared upon R. Yeah. And also, right, we need to realize what is the direction of this acceleration. So we know, right, that A is a vector. And delta V is also a vector. So A's direction, right, is the same as the delta V's direction. So let's look at this diagram here again, the red and blue triangle. So you can see, right, the delta V, right, is the angle, right, that is pointing towards the center. Because the red arrows are the tangent, and the delta V, right, is actually pointing towards the center. So acceleration, right, for circular motion is always pointing towards the center. So you see, why is that so? You can think about it quite visually, okay? By Newton's first law, right, if something is going originally in a circle, right, if there is no center pulling force, right, what would this guy do? He will try to go off tangentially, or he wouldn't go to the next point in the circle. The fact that it goes to the next point in the circle, right, means instead of being, let's look at this diagram. Let's add some points here. Suppose, right, you're talking about this point, its initial velocity, right, is like in a tangential direction, right? So if there's no center seeking force, right, it will want to be here, okay? It wouldn't want to be on the circle. The fact that it's on the circle, right, means someone has tucked it inwards, okay, preventing it, right, from going off tangentially. So how is the tuck being performed? It's tucked towards the center. Someone pull it towards the center, okay? And once you understand this, right, later on when you are doing with gravitation, you understand why, right, for example, moon experience weight, but it doesn't fall down towards Earth. Yeah. And that weight, right, that gravitational pull by Earth on moon is exactly what is needed for it to go in a circle. So instead of it's actually always falling in, except, right, it is falling into the next point on the circle path rather than falling straight down, okay? Because it has a certain speed. So it's trying to fall, but it never managed to fall closer. It only fall into the next point on the circular path, onto the next point on the circular path, and so on. So when you link up all these points, right, it turns out to be a circle. Okay, let's go on. Centripetal acceleration related to centripetal force, in which way? Simply F equal to ma. Yeah. And usually in problem solving, right, the key is to select the correct form to use. Is it this form or is it this form? Yeah. Some points to take note. Okay. When you are solving problem, right, you are always keen to draw the free body diagram and sum up all the forces, okay, in the radial direction. Okay. And note that centripetal force is not a new force. Yeah, it is a net force. Therefore, right, you don't draw it in the free body diagram. It is due to the all other forces acting on the body. Yeah, the net effect. With that, right, let's go into the two types of circular motion that we always are interested in, which is horizontal and vertical. First question to ask, right, is there work done by a centripetal force? Okay, this question is a bit not too good because, right, it makes you feel that centripetal force is like a physical real force, but it's actually not. But never mind. Okay, so what this question is trying to say, right, is there any network done when you have just a centripetal force? Answer, right, is no. Okay, why? Centripetal force is always perpendicular to motion. So when you have an object that's here, the path is like that, right? The motion, right, is always, right, in a tangential direction. So it's here the next moment, but the force, right, is this way. So there's no work done because they are perpendicular to each other. Yeah. So that is the definition of work done. Force times distance move in direction of force. If there is no work done, right, there's one more implication. So sorry, I have to load again. By the way, right, this Microsoft whiteboard is free of charge. Okay, I think I reckon, right, it's one of the better free whiteboard based app. So next time if you are doing project, right, you need things like this, you can consider this app. So I was saying, right, that there's one implication, right, of centripetal force not doing work. You see, from WEP, we learned something, right, which is called work energy theorem. Give me a minute, let me get something. Which is right. Change in KE is equals to, oh dear, why is it like that? Sorry. Change in KE is equals to the sum of all work done, which is net work done. How do we understand this? This is to say, right, that if you treat the real energy of an object, right, of a system to be just associated with its motion, okay, and its momentum. So the only real energy, right, that you can really associate with a KE is with an object is the KE. Obviously, is half mv squared or p squared over 2m. So it's something real. It belongs to the object. Whereas, right, even ideas like PE, PE is just an invisible store of KE. Yeah, when you throw something up, right, the KE disappear. As it falls back down, KE reappear. So it is a way, right, that we invent to account for the KE going missing. Yeah. So if we just say, right, KE is the real energy, yeah, and everything else, right, are just considered as work. Okay. Then, right, the net work that you do on an object will result in the object's KE being changed. So if you have done a net work on a box, for example, you apply a force to push it, right, its KE will increase. Yeah. And that's what this equation means. Therefore, right, applying this equation, right, to the idea of work done by centripetal force. If centripetal force does no work, okay, this means, right, that the centripetal force can't increase KE. Ayo, it's not reading my words so well. I have no reason, no idea why that's so. Yeah, I'll tidy up the handwriting when before I send over later on. Yeah. If you can't increase KE, right, or can't change KE, means, right, speed wouldn't change. Speed will be just constant. Yeah. So this is the implication. So centripetal force, right, has no way of changing speed. Yeah. And that is in line, right, with whatever we understood, because this centripetal force is just to change the direction. So it's not its job to change the speed. So now, right, let's differentiate the vertical and horizontal circular motion. Horizontal circular motion, right, I mean, it's straightforward, right, because it's on the same level. It doesn't go up and down. Therefore, right, there's no change in the GPE. And if, right, this object has a fixed total energy and there's no change in GPE, right, means that the KE will remain constant as well. Okay, this logic you need to understand, because, right, this is the watershed moment, right, between the two horizontal and vertical circular motion. Yeah. Horizontal, same level, GPE constant, so KE constant. So usually, right, horizontal circular motion is a uniform circular motion, because uniform means, right, same speed. Vertical, on the other hand, right, the height keep changing. Yeah. So total energy, if stays the same, then, right, KE will also keep changing. So speed is never constant. Different position have different speed. Yeah. Therefore, the circular motion is usually non-uniform. Okay. Is this way of thinking about horizontal and vertical circular motion, right, familiar to you? Are you used to understanding it this way thus far? Or sounds strange? No? Okay. Without further ado, right, let's do some problems already, some examples, okay? But first, just go through the key steps, okay? Problem solving steps for circular motion. Always, number one, right, draw free body diagram, okay? Number two, these are really like steps, or it's not saying, oh, guidelines, or like very vague kind of things. It's real steps. Next, right, form equation. Once you draw the free body diagram, you label the forces, you know what all the forces acting on it. You know, right, things that go in a circle must have a net force to the center. Yeah. So when you draw the diagram, right, you may not know which force is bigger than the other. But you know, right, whoever point to the center must win the one that is pointing away. Something like that, because the net force must eventually go to the center. That is the logic, okay? And with that logic, right, then you form the equation. So you take the longer force that's pointing to the center, minus away the smaller one that's pointing away. That gives you the net force. And you equate that with V square over R or R omega square. Yeah. Depending on what, maybe they give you information about the period, then you use R omega square. Or you want to find the period, or you use that version. They give you information about the speed, you use the V square over R. Okay. In cases, right, where net force is not in the radial direction, or are there such cases? There are, okay. When I say bracket here, right, very rare, it doesn't mean, right, it is very rare in real life. It simply means, right, it's very rare in exam. You won't be asked to do this. Or it is not rare, or later on we can go through very briefly, right, without confusing those who are struggling with this topic, okay, for the interest of the rest. So let's start off with a simplest horizontal circular motion, which is a pendulum, okay, conical pendulum that's going in a circle like this. So you got to identify, right, conical pendulum is going in a horizontal circle. Horizontal circle, right, one characteristic is all positions, all positions, right, are identical. There's no preference one. Words can't come out. I don't know why. Just be patient with me. Okay. So you can just consider any one of them. So let's consider this position. You draw the forces, mg. Then, right, here is tricky because, right, you actually don't see any force, right, which is directly towards the center of the circle. So that's where you need to resolve, okay? So let's call this one, right, force in a string, Fs, okay? Because I don't want to call it T. Symbol T later on we need to use for period, yeah? Next up, right, is we want to resolve this Fs. So we know this one, right, to be resolved, right, vertically and horizontally. This angle, right, is also theta, okay? Therefore, right, you can start to form equation already. So in the y direction, you will have, let's just call it F lah. Skip the S. F cos theta equals to mg because there's no net force. So this is like equation 1. Then in the x direction, okay, you have F sine of theta. Here, right, you can write two forms. It could be mv square over r or mr omega square. So let's do one first, mv square upon r. Okay, equation 2. Characteristic of horizontal circular motions equations, right, which are formed this way, is that F, right, is usually irrelevant one. Okay, because when you take equation 2 divided by equation 1, the F will disappear. So you left with tangent theta equals to v square upon rg. Yeah. So with that, right, you have the relationship between v and theta. Okay. So you can go and tidy up, right? So you will have v square equals to rg tangent theta. So v equals to square root of the whole thing. Done. Okay. So it's pretty easy. And next step, right, we want to find the period. So we will write, right, the second equation, right, with in the other way. So f sine of theta equals to m r omega square. Okay. And this is equals to m r 2 pi square over t square. Okay. Yeah. So we can hence, right, do the same step and solve for t. So now, right, I don't want to continue with this one because I'm having a lot of trouble writing on this platform. So you can go and try it yourself. Yeah. And that's literally, right, the ABC of how to solve problem of this type. Problem of this type, right, can appear in many ways. For instance, instead of having a pendulum, you could have, right, a motorcyclist. Okay. Can you imagine, right? This is a motorcyclist, okay, and is making a turn, okay. So the forces, right, actually look remarkably similar. You will have mg, and you will have a contact force that goes this way, okay, and we call this R. Why I call this R? Because it's not a normal contact force, it's a contact force. It comprises the normal component, which is the R. It comprises friction towards the center of circle. Yeah. So you can see, right, the free body diagram is similar to the conical pendulum. Also, you will have the airplane kind of problem. Airplane, whenever they turn, right, they need to bang towards one side. Okay. So the forces, right, once again, are really, really similar. Okay. You have mg, and you have the lift force, which always acts perpendicular to the wingspan. Yeah. So once again, you see the free body diagram is similar. The equation you form will also be similar as well. But there's a difference, okay? For example, right, the context of matter, usually, right, in cases like this, you solve for V. You don't solve for period because, right, period is irrelevant. When a car want to make a turn or when an airplane want to make a turn, it doesn't turn and turn and turn and turn on the spot, right? Or in a circle, right, forever. It turn and go, yeah, as part of its maneuver. So you are interested, right? What is the speed needed for a particular radius? Yeah. And maybe also interested in the angle that you need to bend it, okay? But you wouldn't be interested in the period. So period will be more associated with, let's say, conical pendulum, because you may do an experiment and that is what it's doing, going in a circle. Yep. So let's answer, right, yet another question. Question, why do the car, right, ski when it go into a bend with too high a speed? This is not difficult to answer. So let's redraw this, right? In terms of the road level, you see this terrible diagram. So let's draw it, right, when we are looking at the car from the front. So you have this is mg, okay. Then you have a normal contact force. I'm just going to draw, right, from the center. By right, you're supposed to draw from the wheels, but never mind. Then you have the friction. Yeah. So why do cars ski? First and foremost, right, you must realize, right, that when car go into a turn, normally, right, before it go into a turn, right, the friction actually don't act this way one. It's only when you want to go in a turn, right, then the friction starts to act from the sideways towards the center of the turn. Why is the friction like this? Because of this key characteristic of friction is a on-demand force. Okay, and this force, right, this friction, right, is actually a static friction. Yeah, this is a static friction. There is no relative motion between the car tire, right, and the direction of friction and the direction of motion towards the center. There's no such motion. So this friction, right, exists, right, in a static way. Okay, it's like preventing the car from moving outwards, but it didn't arise because of car rubbing the tire, right, against the road, like in the radial direction. So it's a static friction. It comes in simply to provide for this circular motion. So you will have, right, this friction equals to mv squared upon r. Okay, so you got to realize, right, that this friction, right, is really on demand, because you can ask, right, it's the same road, same radius, okay, cars come in with different speed, and the car also have different mass, right? Not so, right, whatever the mass is, whatever the speed is, the friction will try to provide. Okay, but friction, right, always got a maximum value. Okay, that is the maximum static friction. So it is subjected to this value as long as, right, your mv squared upon r is less than this maximum static friction, is okay. You will provide for it. But, right, if this value is breached, then it's not okay anymore. Okay. So suppose, right, you go in a car band with too high speed, okay, such that the mv squared over r, right, this value is larger than the static friction, maximum static friction that can exist. Then, right, this circular motion cannot take place already. Yeah. So that is what is meant by part one. So the mv squared over r too large, larger than the maximum static friction. But still, we cannot explain why does it skid. The reason it skid, right, is trying to increase the r. Okay, you see, I go into the band with a certain speed already, but if the friction cannot provide for this particular turn, right, that I'm performing with my speed, then, right, what seems to happen, right, is my car will simply find a new circular path, okay, with a larger radius that can allow that friction, right, can provide for. Okay, so if a particular radius cannot, so the car will go into a larger radius so that can find a new radius that can be provided by the static friction. Or thus, right, if you go into other radius, right, what are you doing? Skidding. Okay, let's draw it, right, to make sure that you understand what I mean. So this is the road. The car is supposed to be here, okay, and this is the particular radius. It's called R1. But if, right, speed is too high, it cannot. Then, right, you will try to find another radius, which is R2, whereby, right, under the current speed and the current static friction can provide. But relative to the car, this guy, right, will have skidded. Yeah. Second part, not too difficult. When the road is wet, the maximum static friction will decrease. Okay. Thus, right, the speed that it can support, right, the maximum speed that it can support for cars, right, going into the bend will be lower. So when cars exceed that speed, they will skid. So far, so good for this portion. Is it too difficult? Okay, so let's go on. What about, right, this situation? Why are roads banked at the bend? This is called banking. You actually see this all the time. Whenever, right, you have a car going into those kind of enter an expressway, or always got a roundabout, right, or exit from an expressway, always got a roundabout. The next time you travel on in your parents' car, notice the road is actually slanted one. Okay, slanted from the side. So why is this so? I will not try to do too much math here. Just show you the simple idea. This normal contact force. This is friction. Okay, and you have mg. Ayo, I'm sorry. Yeah. So you see, how does this look different, right, from the previous diagram, whereby the road is flat? Which is, right, along the direction of along the direction towards the center, you will see, right, that, hang on, this thing doesn't close. Okay. Along this direction, right, you see, right, there are now two forces acting. Now you have a normal contact force also slanted, okay, slanted towards the center. Friction also slanted. Friction originally was the only one that's providing. Now, right, only a fraction of it can provide. Like it's like less good, right, compared to before. But now, right, you have another powerful ally, which is the normal contact force. Okay, normal contact force now also have a component of itself, right, towards the center of the circle. Therefore, right, the shortage of friction, right, because now you have only a component of it, is more than made up by the presence of the component of normal contact force towards the center. Therefore, you can support a higher speed, given everything the same. Okay, same radius with banking, this road, right, can support a higher turning speed. And this is why, right, banking, that's why I say all the roads, right, entering and exiting expressway, right, especially exiting expressway, must have banking. Because, right, when they exit expressway, they may still be moving quite fast. And if not bank, right, and the road is slippery, they will skid. So it's to use normal contact force, right, to provide more support for the circular motion to occur successfully. Okay, don't worry too much about the math for this. This is too complicated, very hard to solve. I will tell you, right, when are things, right, you must know one, and where are things, right, which are good to know. Okay, in exam, right, not so important. So that one is good to know. Now, right, let's go into vertical scalar motion. I'm running a bit slow. Okay. Let's figure out, right, what's the normal contact force on the roller coaster at these two positions. Okay. Before we know anything or we figure out anything, right, let's always draw in what we know, which is, right, usually just the weight itself. If we know the weight, right, that would be pretty good already, right? So that is like first piece of the puzzle. So this mg. Now we know, right, that the net force in a circular motion must always be towards the center. Okay, not true for vertical though, but it's fine. Okay, that will suffice for just that statement will be correct, at least for these two positions. So net force must be toward the center. So at the bottom, right, in order for net force to be the center, the normal contact force must be this way. Okay. For the top, in order for net force to be towards the center, actually, right, no requirement. Oh, no requirement, because there's already mg that's towards the center. So even if there's no normal contact force at the top, you ask yourself, is it possible, right, that it can still perform circular motion? Oh, answer is yes, because, right, there is already a force there. You don't need, right, normal contact force to be there as well. But right, let's just have it here first, okay? And let's call it N2. So how do they compare? Let's write out the equation as well. So the speed here, right, let's call it V1, and here V2. Which one is bigger, V1 or V2? Let me call someone. I thought until very bored. Let me call those names, right, I don't know personally, so I can chit chat with them. Oh, who is Ruth? Wow, as I call her, she suddenly disappeared. Okay, never mind. What about Charlene? Charlene with a start with S. Huh?
Sorry?
Yeah. Hello, Charlene.
Hello.
How does V1 and V2 compare for a roller coaster? Which one is bigger?
V1.
Why so?
Because if V2 is bigger, then but sorry, cannot.
I give you a clue. Go from the angle of conservation of energy.
Oh, is it a V2 is the KE become GPE already?
Yeah. Oh,
okay.
But what is the assumption for this to be valid?
Assuming no external.
Yeah, you're quite good. You're on the correct track. What kind of force could be there to cause this not to be valid? You think like a roller coaster moving on the track.
Resistance.
Yeah, very good.
Okay.
So assuming no friction. And this assumption, right, is usually built into the question. They will tell you, right, the roller coaster going on a frictionless track. Okay, frictionless vertical circular track. Yeah. Okay, thank you, Charlene.
Thank you.
So V1 larger than V2. Yeah. So you can write out the equation. At position 1, you will have, right, N1 minus mg equals to mv1 square over r. Okay. Then, right, N1 is equals to mv square over r plus mg. Okay. Then equation 2 is, right, N2 plus mg equals to mv2 square over r. You see, you're just converting what you see on the free body diagram into the equation F equal ma. Okay. Then, right, what's next? you make n the subject once again, and you can see, right, some things starting to appear. You have mv2 square over r minus mg. Okay. Hence, right, comes to the second part. How do these two normal contact force compare? Which one is bigger? From the diagram, right, you can conclude must be n1. But from these equations, right, you can be definitive about it. Yeah. Because you see, first one, right, n1 is equals to a particular mv square over r plus a mg. Second one, right, is a particular mv square over r minus a mg. One is plus, one is minus. Of course, the plus one is advantage, right? Because you plus mg. So it's like bigger, right? Then you need to ask, right, what about the first term? Oh, this one, right, v1 is large. So the first term, right, is already larger. Whereas here, right, v2 is small. So n1 is confirmed bigger than n2 because it is a larger mv square over r. Furthermore, plus a mg. n2 is a smaller mv square over r. Furthermore, minus mg. Okay. This logic, right, will come in very useful whenever, right, they want you to predict. Okay. Suppose, right, you have a rod connected to a pendulum bob. Okay. Then, right, here is a glue, for example. Then this thing is swung in a vertical circle, faster and faster and faster. Okay. Then they ask you, predict which position, right, is the glue most likely to give way. Does it sound familiar to you? Bound to have done something like this before. The logic is exactly the same as whatever we have done in analyzing the normal contact force. But instead, right, you'll call it force by the glue. Okay? You just call it F. So bottom position versus top position, F1 and F2. Then you do the same analysis and you come to a conclusion. At the bottom is more likely the glue may give way because, right, the force by the glue required at the bottom is like larger. And the glue, right, has a fixed maximum. So where is it more likely that you'll breach the maximum that it can provide? You'll be more likely to be breached at the bottom. That is the logic. We continue circular motion, but vertical. But now, right, let's look at something called the limiting condition. Limiting condition, right, is something that's only for vertical. Okay. What does it mean? You can try later on. Okay, if you have a pendulum bob, right, something that has a string and a mass attached to it, right, you need to swing. You realize, right, when you swing too slow, the string, right, will become lembek. Okay, before I reach the top. Or lembek means it becomes slack. So it's like somewhere here, then it goes slack already. Once it goes slack, right, then it cannot continue the path. So can't reach the top. So there is a particular condition, right, that you must fulfill for the circular motion to be completed. Okay. I.e., right, for the string to be still taut at the top. Or it cannot go slack at any point. It must always remain taut. Taut means what? You have a fixed radius. Once the string becomes slack, right, you see the radius, right? Sorry. There's no longer any radius to talk about already once the string becomes slack. Okay. Thus, right, let's analyze this scenario. So what happened, right, at the top? Okay, we draw a free body diagram. You have, hang on, change color. You have mg, okay, and you have t. Let's label this. This is top. I need to get an iPad lah. This one, my tablet, right, is cheap one, not too good. Okay, so let's try out the equations, right, relating the T, the mg, and of course, right, we also need the velocity at the top. Let's call this, right, V1, okay? At the bottom it's called V, at the top it's called V1. So we relate this few together. So you will have, right, T plus mg equals to mv1 square upon r. Okay. Now, v1 square, right, and the speed at the bottom v square, how do they relate? Oh, you know, right, that the top and bottom, right, you can always use COE. Okay, so top and bottom, right, you see the loss in KE equals to gain in GPE. Yeah, so loss in KE is how much? It's half m v square minus v1 square. Okay, and this is equals to mg2r. Or the h is just 2r. So with that, right, you can actually relate, right, v1 and v. So v1 square is simply equals to 2gr plus v square. Okay. Did I get the math right? No, it's 4gr because the half have to multiply over. Yeah, you can check the math later on. So, but this is not the crucial part. This is just relating v1 to v square. So now, right, we can substitute this back into equation 1. So equation 1, right, will look something like T minus T plus mg equals to m over r 4gr plus v square. Okay. And let's make T the subject. So I don't want to write another line. So let me erase away the term on the left. So T is equals to this one minus mg. And we know T must be greater than 0. Why? Because, right, this is what it meant by to be taught. Yeah. So if this is the condition to be taught, right, then you have an inequality to solve, okay, to tell you what is the condition for V in order for the T eventually to become taught at the top. Oh, sounds quite a mouthful, but let's just solve it, okay? So with that, right, you can just cancel away all the m. So you have 4gr plus v square is greater than gr. Okay. I must have made a mistake somewhere because, right,
Mr. Clark, I think it's the first equation. It should be v1 square is equals to v square minus 4gr.
v1 square equals to
v square minus 4gr.
Oh, right. So it's here is a minus. Okay, can already. Thank you for spotting this. So minus here. So you have v square greater than 5gr. Okay, so you see, this tells us, right, there is a condition imposed on this system. If you want it to perform the circular motion completely, right, the string has to be taut at the top. So that means the tension at the top must be greater than 0. And you can relate the speed at the bottom to the speed at the top using COE. Okay, and hence, right, you can solve for the inequality involving the V. Okay, so this is something that is common of vertical circular motion problem, finding the limiting condition. And you must solve using, I mean, not say you must. Usually, right, in school, I think, right, many of you solve it by putting t equals to 0. Not so good, because, right, limiting condition got two types. It can be, right, you cannot move too fast or you cannot move too slow. Oh, let me give you an example, right, for the second type. Suppose, right, you have a car moving over a hump. Okay, this part is just a curvature. This is not a like a semicircle or what. Or the radius of curvature is actually quite large, like go all the way to the bottom. Yeah. So at the top, right, this car, let's look at the forces acting on it. So you have mg and you have normal contact force. I have already drawn, right, normal contact force to be smaller than mg, because I know that net force must be to the center. Or this logic must be apparent to you in all situations. Because it goes in circular motion, it must have a net force to the center. Yeah. So with that, right, you're right. Mg minus n, okay, equals to mv squared upon r. And you will write n as a subject, and you will have, right, mg minus mv squared upon r. Sorry, the things don't appear, not even on my screen, you know. So I'm writing in like blank, and I hope that the words will appear, and it doesn't. So let me write again. Yep. So this is greater than 0. So you will have, right, v squared upon r must be lesser than g. Okay, so v will be smaller than square root rg. Okay, so this is a limiting condition, right, which tells you in order not to lose contact with the ground when you are like driving over a hump, right, you mustn't go too fast. Okay, because, right, this inequality follows from the n must be greater than 0. So it is like a consequence, or it's actually a precondition of linking the condition for f, a condition for v, and a condition for n. V cannot be too fast, otherwise n cannot be greater than 0. I have a problem here, the roller coaster one, which I will not go through because it will take quite some time. It's inside the MCQ set, so you can go and practice. Okay. Lastly, right, we'll go through one final case, which is a uniform vertical circular motion, which is like a standalone kind of case. Yeah. And we'll use just one example to illustrate. So this example, right, no need to perform any calculation, only draw arrow. So how do we draw the forces, right, acting on the man at all positions? As usual, right, we'll draw in the most obvious force. Okay, which is mg. Next, right, let's study the straightforward positions. So at the top right and at the bottom, we already know it quite well. So at the bottom right, the normal contact force has to be slightly longer than, why like that? Let me try again. Or slightly longer than mg, so that right, it can provide a net force to the center. And at the top right, is like slightly shorter than mg. Okay, slightly shorter than mg. And if you actually put a weighing machine, right, and you stand on it, right, you compare the weight, okay. At the bottom, you'll notice, right, your weight is a bit more than your normal weight, your true weight. Whereas at the top, it's slightly less than your true weight. Oh, that's the reason why. Because the n is different. Let's study position B. Position B, right, this n is exactly equals to mg. Yeah. And what provides for the circular motion is, right, something else already. Okay. And because this is position B is exactly, right, like to the left of the center, so it must have a horizontal force acting on it to provide for this. So that force, right, must be like this. So this is the friction. Okay. Position D, right, will be very tricky already. Okay. Why so? Because, right, you want a net force, right, to the center, and it's like somewhere diagonally. So how do we have that going? So here, right, will also be you also have a normal contact force, but this time round, right, okay, this one must be slightly lesser than mg. Yeah, sorry, I'm not sure whether is it my tablet or is it my or is it this app. Okay, so slightly less than mg, and the friction, right, will be to the left. Okay, like that. I think, right, one point about position D, right, that is not too clear. Why is it that the normal contact force, right, is actually slightly lesser than mg? Why can't it be just equals to mg? Well, reason is because, right, net force needs to be this way. Yeah, net force needs to be in this direction. Ayo, why suddenly exit again? I think it could be the content too much, and this thing is loading very slow. Just 1 minute. Okay. Yeah, I was saying, right, at that position, right, the logic is net force must be to the center. So it must be along this dashed line, right? So you consider, right, friction is to the let's magnify this, okay, and draw it again. So friction, right, is like this way. Yeah. Therefore, right, the resultant of weight and normal contact force, right? So you combine weight and normal contact force, right? The resultant of those two, right, must somewhat be downwards, okay? So that, right, the resultant of those two with the blue arrow will be towards the in the line of the black dash line. So let's call this, right, like mg minus n. Yeah. So this is the reason, right, why n must be slightly lesser than mg at that position B. Okay, so this more or less, right, sum up all the concepts and ideas in circular motion. So the last 5-10 minutes, maybe you can ask questions. Any part I wasn't clear, we can clarify. Yeah. Anyone?
Mr. Kai, can I ask about the small angle approximation part?
Oh, yeah.
Can you explain why delta V is approximated to V times delta theta? Like the
Oh, yeah,
first
yeah, yeah.
statement.
You see the magnitude of BA and BB, right? This one is actually equals to just V itself. Sorry, it's getting very slow. So the side of the triangle, right, is like of length B. So it's a isosceles triangle. Oh, and the third side, right, is your delta V. So how long is the third side relative to your two other sides? Well, the math to do this, right, is given by the way, right, that we can find out what is the chord length of a small sector. The chord length of a small sector, right, which is the straight line, right, that connects the 2 points on the arc, will be almost equal to the arc length. And the arc length, right, is given by r times of theta. So ds here, right, is the arc length. Yeah. And if the arc length is almost equals to the chord length, right, so the chord length is simply r times of the theta log. Yeah. R times of the angle. Similarly, right, in this triangle, the third side, right, is also the R, but now it's not R, it's just a side of the triangle, which is V. So it's V times of the theta.
Wait, so do you like you differentiate, is it?
Yeah,
Because
you don't need to differentiate per se because, right, this is already a very small, I should write this, right, as a delta, it will be better, okay? It's like a very, very small change in the velocity, yeah, arising from a deviation, right, from point A to the next point, just very little only. Yeah. Therefore, right, all we are doing here, right, is we are just taking this small change in the velocity divided by the short time, right, that this change is taking place over. And you have the d theta over dt, right? It's simply omega already. Okay. Quite a lot of concepts here. Like always, right? I urge you to look through this and persuade yourself again, right? Explain to yourself again different parts. Okay, go through the whole cycle one more time. This time round, not by listening to what I say, but you figuring things out by yourself and can say outright, articulate out the reason behind it. Then you will have understood. Okay. Yeah, without further ado, right, I think we can end the session here. Those who wish to ask questions, right, can stay back. Okay. And the rest, right, could just go ahead. Have a good afternoon. Thank you and see you.
Thank you, Mr. Craig.
Thank you, Mr. Clark.
Thank you.
Mr.